Okay, so we are beginning our new unit today on modeling quadratic functions now. We've done quite a bit with it. This is the last we are going to do. So our learning goals, I can determine the maximum or minimum of a graph quadratic function, determine the domain of a graph quadratic function in a real-world context, identify initial height of objects when given a quadratic function or graph, and connect information in a table to key features of a quadratic equation, and interpret their meaning in a real-world context. So again, that's lots of words there. But by the end, I do want you to kind of come back to this and make sure that you're like, okay, yeah, I know what that is now and I can do that. So, and if you can't, go back, see if you can figure it out. If that doesn't help, then that's when you come to me with questions. So, graphs of quadratic functions representing real-world scenarios. So, vertical motion equation, which you're going to see a lot of and have seen a bit of. It's h equals negative 16t squared plus bt plus s. Describes the height of an object after t seconds. So again, this is height here. Okay, t is time in seconds. You get the idea. Okay, what do you think v is? Velocity. All right, and we'll get into the rest of that in a little bit. So, what is the total number of seconds the ball travels? Simple. All you have to do is look at your graph for time, because this is time in seconds. Where does it start? It starts at 0. It ends at 2 seconds. What is the maximum height that the ball reaches? Well, that's right here, right? So if this is 8 and this is 16, that means that each one of these is 4, which means that this is 20, and it shouldn't be meters. I'm so used to our physics class. It should be feet, because that's what the height is in. And then finally, how many seconds does it take for the ball to reach its maximum height? Its maximum height occurs at right here. All we have to do is go down and look, and it should be half of our total time it's in flight, which it is 1 second. Okay, easy enough. Example 2 is an engineering project. Your team is drawing a highway tunnel on a coordinate system. The tunnel opening is in the shape of a parabola, so that's this shape right here, in case you can't see it as well on your screen. What is the total horizontal distance from the base of the tunnel? So horizontal, we're talking about from here to here. Remember, horizontal is across. Now notice that this is negative while this is positive. So that being the case, what you always want to do is take the one that's farthest to the right, subtract the one that is farthest to the left. So in this case, you're going to end up doing 20.8 minus negative 8, which, as we all know, is 20.8 plus 8. And when you add those two together, you get 28.8 feet. All right, next example, you throw a ball straight up in the air. So basically, we're going back to this one here. Okay, so this is my rendition of the graph. From what height is the ball initially thrown? So here what we need to do is we need to take a look at our graph. So initially thrown, because things we have to remember, our x-axis is time. Time can't be negative. So even though our graph technically does all this, time cannot be negative. So we are throwing, even though the graph does extend in this direction, since time can't be negative, this technically doesn't exist. Which means the starting point of the ball is right here, which if this is 8, this is 16. Remember, we said these were going up by 4s. So that would be 4, 2 seconds. That's not right. That's not right. It should be, of course, 4 meters. Okay, so hopefully you're not just breezing through this, you're reading it. It should be 4 meters. Because that's where it started from. It's initially thrown from 4 meters up. All right, man throws a ball off a tall building and records the height of the ball at different times. So that's what this is. T is time, h of t is height at that particular time. What can you learn by finding the graph's intercept with the h-axis? So again, if we were to sketch a graph of this, okay, so when t is 0, h of t, which in this case is like our y-axis, is 46. Okay, and then after 1 second, it's up at 63. And at 2 seconds, it's almost back to the same height. 48, and then at 3 seconds it's almost all the way down here. So what could we learn by finding the graph's intercept with the h-axis, which is this one up here, t is over here. So with the h-axis, we can find the height at which the ball was thrown from. That's this right here. So it was thrown from a height of 46 feet. Intercept with the t-axis, so this right here. So basically where it would cross would be the amount of time the ball was in the air or how long it took the ball to hit the ground. So since this is time down here, when it intersects with there, that means it stops moving. So all this time is where it is in the air until it hits. Okay, last but not least, the values in this table represent the relationship between revenue in thousands of dollars, R, and the price that is set by the company, P. Data is approximately modeled by a quadratic function, which you're not given. That's fine. We have a table. That's all we need. Does a function have a minimum or a maximum? Well, if you look at this table and imagine, okay, so again, I can sketch a small graph. Be like, well, that would be like 0, 0 right there. And it comes back down at like 33. Okay, remember these are like our x values. These are like our y values. So when x is about 33, it's back down to 0. So somewhere around exactly in between that is going to be its highest point. So because it starts here, and then notice as our x values go up, our y values go up initially. Okay, so that means this parabola is moving like this. And then notice as soon as you hit that 16, and that's actually not 16, 0, I don't know if you can read that anyway. Once it hits there, the values of y start to decrease. So they're increasing here, they hit this point, and then they start to decrease. Okay, so this would mean that it has a maximum. It has a highest point, not a lowest point. It has a maximum. We want to identify what it is. Well, according to this graph, the highest that we see is 300 for our y, 16 for our x. So what that means is, okay, if R is our revenue and P is our price, when the price is set at $16, the company's revenue is $300,000. So that's essentially what you're looking for is, okay, is this the highest point? Yes, this is the lowest point, but we can tell that this graph looks like this. So even if this was not a real world situation, it would just keep going, which is why we say this is the maximum this graph can reach. Okay, so that's what that means, and then our x value is price. So that's when you say when the price is set at 16, the revenue, which is the R, is set at $300,000. Okay, the intercepts is where it intersects the x-axis. So it's 0, 0, and 33, 0. And what that means is when the price is 0 or 33, our revenue is $0. So it means that the company has no revenue when it sets its price at 0 or $33. All right, so kind of a lot to take in. Not a ton of math, really. This is just learning to read and interpret these graphs, and the only way that you're going to do that is through practice and through asking questions. So if you have any, please don't hesitate to let me know. Thanks, guys. You have a good one. Take care.